It's good to be back to Princeton, the summer school. I didn't know that it was actually 17 times already. All right, so okay, let's drop this. Okay, good. It's good to be back here, and it's also good to be back into the in-person summer school. I think that's kind of so nice. I think one of the nice thing about the in-person, especially in-person part, is we can make the close interaction. So I prefer to be interrupted in the beginning, although also we can just make the longer discussion toward the end of the presentation or lecture. But also I don't mind you just kind of breaking in any moments and ask some questions for the clarifications, or even more discussion. I tried to make my slide not too long, expecting that we have rather interesting discussions. I'm going to give you the two lectures this morning, the first one and second one. And the first one, I think entire theme of the school is hidden symmetry, hidden order. I forgot. Hidden something about flat band system. I think most likely that we will hear a lot of the lectures on the twisted bilayer or twisted Van der Waals system, which actually has been one of the focus. I'm going to give you some part of my perspective on that side, and refer that many things that more in depth and the detailed discussions in later lectures, like with Dmitry will give us some lecture. Also, this multi-layer side, I see that Steven Najpozi will give us also lecture later in the school. So we'll hear about kind of many things. So let me see that I can just put down a little bit of groundwork, a little bit, bring you back to some of the old work as well. And the second lecture is a little bit tangential in some sense, that the topic that mainly discussed in the school. Second lecture is related. First lecture in terms of atomic scale of the reconstructions, which I feel like, at least I believe that is important ingredient to understand this Van der Waals interface, especially this the Morales system. And hopefully that will also make some connections of the interesting part and perspective. So that's kind of structures. So let me start with the first part. I just try to give you the talk about the flavor symmetry breaking and correlated states in the twisted graphene multilayer. And you will see that what I mean by the flavor symmetry and how those kind of things related with correlated states in this twisted system. Okay, so main part, I will just kind of use a little bit of the background, but then I will just use some of the experimental results came out from my group as well as some part in the other groups. And the result of my groups mostly coming from this four students postdoc, especially Xiaoming Lu, who is now in the Princeton as a postdoc working with Ali Azani, got a lot of initial work and theory collaboration with Ashwin, the team coach school. Okay, so the graphene is basically a model system. We are going to hear that a lot of the different lectures, including my lectures. Graphene, of course, has been around for a while now, and it serves as a good, in some sense, simple but yet kind of rich material platform to realize some of the interesting physics we are going to talk about. And the simplest in mind, if you just put the simple tight binding model to compute the band structures, especially low energy band structures, we are mostly concerned. I think that the dispersion relation is linear, and there is already considering the crystal symmetry. There's hexagonal shapes of the first Brillouin zone. At the corner of this Brillouin zone, basically this Dirac constant sits in there, right? This has been figured out already in the 1940s. That Philip Wallace's the calculations. It turns out that effective Hamiltonian to describe this low energy excitation near the this drop point, where actually naturally undoped graphene fermi level is, can be expressed in terms of this 2x2 matrix, where you use a basis for this the two PZ orbitals sitting in the one carbon atom, A sublattice and B sublattice carbon atoms. And quickly that this the effective Hamiltonian, you look like that half of the Dirac equations or wide equations, where that each of the value carries a different signs of the destiny. I think this story has been around and served as a good but rich the physics system one can see that somewhat different from the typical band structures we know in the massive carrier system, like the semiconductor metal, and provide us kind of good platform to realize many different layer the topological system I'm going to briefly touch upon. Now, effective Hamiltonians they look like the equations under the magnetic field. They also developed the Landau level, but as you already figured out in the 1929, I think Rabi actually already solved the Landau level in the Dirac dispersions. But anyway, the full point here is that this Landau level has one special Landau level sitting right at the zero energies, and that will basically shift this the sequence of the quantum plateaus, such that quantum plateau can be represented by this. Let's say that if I look at the Rxy inverse or the sigma xy, that's 4 times of the half integers, and this half integer is basically indicating there is unique Debye phase associated with the electrons into this spectrum, and that has been another important part, the kind of constituted unique part of the graphene stories. What is important today is that in fact, when you just write down this type of band structures and dispersions, there is the degeneracy that going with the single particle dispersions. Degeneracy, in a sense, we didn't consider anything about the spin in this picture, and since spin-over coupling in the graphene is very weak, spin is simply just a degenerate without magnetic field. With some magnetic field, of course, you have to include the Zeeman energies. But typically, they compare with all of the other energy scale, including electron-electron interaction. Zeeman energy is usually very small, even something like the tens of Tesla level. Therefore, usually you can kind of ignore that, especially system is reasonably disordered, and spin often just comes as a kind of the approximated degenerate systems in graphene stories. Of course, that will change a little bit later. But then there's a two valley exactly sits in the same degeneracy. Part of the reason is basically this there's inversion symmetry as well as the time symmetry protect this the degeneracy of the two valley structures, and this will basically give us that total degeneracy is 4 into the system. Often that appears in the simple integer quantum, that's 4 times of half integer, and that 4 comes from basically 2 degeneracy we are talking about, and that kind of constitutes important symmetry that we have to consider later on. Now, when we have this the quantum degree of freedom, they often just kind of plays quite an important role to detect the interactions. So let's think about the electron with just speed, and then spin. Of course, we have the 2 components we can set up, spin up and spin down. And when we just put the 2 electrons together and total wave function, if you consider, of course, you have the singlet and triplets, and you can consider that this is the systems that we can think about. If there's no magnetic field, of course, a singlet and triplet energies can be degenerated. But once you just throw the interactions between these 2 electrons, well, the singlet and triplet energy can be different. And naive thing that we can just think about is, well, so singlet and triplet, they can have the different magnetic moments, especially singlet is always 0, triplet can be just plus minus 1 or 0, right? So there might be some magnetic interactions we have to think about between these 2 magnetic moments, but turns out that magnetic moments directly coming from spin is too small in the kind of typical energy scale. Nevertheless, once you throw the interactions, there can be strong energy difference between singlet and triplet if you consider exchange interactions. Basically, exchange interaction mediate this Coulomb interaction between them, can create this singlet and triplet energy scale largely different up to the Coulomb energy scale, right? So this becomes kind of relatively important energy scale quickly by just considering this symmetry. But think about here, the spin plays a role of the spin here is not just kind of really magnetic interaction, but it's simply give you the additional index of the wave functions to mediate the exchange interactions, right? If you just think about it in that way, it doesn't have to be the spin. Any degree of the freedom can do this type of thing, right? So, for example, that if I have the 2 layer of the 2-dimensional system, often this is what we call the quantum bi-layer system. If you just put the magnetic field into the quantum states, but nevertheless, which layer that I put this electron, that layer index actually can play very similar role that like the spin indices. right? And eventually it can just kind of act like the spins in special cases that determine the interactions, right? It can be other degree of freedom. I just already mentioned the value on the two graphene, the K and K prime point to two opposite corner of the beryllium zone. That also, that indices can play like the spins role, right? When it goes with interactions. So quickly you can see that this additional degree of freedom, especially together with the spin and valley, can play quite important role when we just think about the interaction into the system, right? And historically, this has been already discussed quite a bit, especially that when you discuss about the quantum Hall system in semiconductor heterostructures, this realized already is an important degree of freedom or important symmetry that we have to consider. For example, this multi-component quantum Hall effect. Say this some of the old work, but basically this is quantum Hall bilayer, and then I mentioned that there is the layer indices that act like the spin. We can call that to distinguish that with the real spin. We can call that the pseudo-spin, and also electron has its real spin, right? So combination of this layer pseudo-spin and the real spins into this quantum Hall bilayer can create this or give you the additional textures that you can just kind of manipulate. And in this particular case, you can create a new fractional quantum Hall state that was not observed in the single layer, can be observed into this quantum Hall bilayer, and this is all. Sometimes you can use the semiconductor has a valley. It's not sitting at this K and K prime like the graphene beryllium zone corners, but sometimes it depends on the semiconductor, especially I think this is aluminum arsenide, worked on here at the Princeton by the Menschel science group. Has a valley, and this valley symmetries can be tuned by the strain. So in this case, you can imagine that spin is coupled with a magnetic field through the Zeeman and make the small splitting. And valley spin, valley pseudo-spin can couple with the strain in these cases by controlling the strain with the piezo. That also you can just control this valley degree of freedom into the system, and showing that spin and valley, the combination of the symmetry can be manipulated in this type of system. So the whole point here is that this additional degree of freedom, pseudo-spin degree of freedom, has been used in the condensed matter systems together with the spin degree of freedom to make this system quite rich, right? So in that regard, I think graphene has a kind of interesting the cases, because now spin and valley that make up this kind of relatively large spin degree of freedom. So that's kind of something that we can think about. Now, in this spin and the pseudo-spin, often that applying the magnetic field, apply the strains and kind of other means that there is the corresponding field that control that these directions of the spins to align, right? Often this is what we can say that anisotropy we given into the system, or the spin anisotropy given the system by the external field. But even without field, we know at least in the spin cases, there are certain materials, the direction got just kind of aligned together in collective way and just kind of completely polarized to form the ferromagnets, or sometimes it kind of becomes anti-ferromagnets. And there's an important concept without even just kind of outside the driving field. Sometimes the spin or the kind of this degree of freedom can align into the one directions and give you some of the ordered states. But often just kind of causes this kind of spontaneous symmetry breaking, and that becomes kind of important tools to understand all this kind of ferromagnets of the system, right? So idea is basically, although the Hamiltonian itself does not contain any particular breaking symmetry structures, the Hamiltonian itself is rather symmetric, and there is no particular directions we can think about. The ground state that basically choose a particular directions to break the symmetry spontaneously, and that's often that important concept to understand this the ferromagnetism, right? And often this ferromagnetism comes as the important the way of the understand the magnets. But now with this the expanded spin space, including this the real spin and this pseudo spin, in the graphene case is values to pseudo spin, we can think about the same things in some sense, right? Although in the real magnet often is the electron spins, which is SU12, that kind of line in certain directions and then break the spontaneous symmetries. Now, when we just think about this combination of this spin and pseudo-spin, and if you just write down spinor structures, that now it should be kind of 4 components, right? Whether it's K or K prime and spin up and down, right? You can think about this as basically 2 block spheres. Each of the spin and the pseudo-spin has a kind of spans its SU2 space. So it's kind of a multiple of this SU2 spin space. But now you have to think about also in some sense, not only just the 2 block spheres kind of multiple together, but there is an entanglement between them. So total the phase space that I have to explain, describe about this state is basically this SU4 states of in the graphene's case, right? And very similar way, like the SU2 spin, the spontaneous symmetry breaking. In principle, we should think about that. Is it possible that we can break this symmetry spontaneously, and that let this SU4 spins that point in some directions? Right? So in a sense that in the graphene, often that can we actually think about this spontaneous symmetry breaking of the SU4 spins, and what is the role of that? Already quite early on in graphene research, this has been really recognized as kind of one of this multi-componentness may actually plays quite important roles to understand that the physics, especially interaction physics, going into graphene. Good example that already appears again that I'm using that giving a talk at the Princeton. I will give you a lot of Princeton results, also important result. This was done, the work that Fong and when Joe Cherkasy was Fong's graduate student, is one of the really nice experiments. This experiment is basically take the graphene, apply the strong magnetic field, and park the chemical potential at the 0 energies, right? So I mentioned that in kind of roughly single part of the picture, so when chemical potential is at the 0 energies, there's always a Landau level in there. It's always partially Landau level, right? And so I don't expect that the quantum Mori effect or anything unusual happens, but turns out that when you just do that experiment, as you apply the magnetic field, that the resistance goes up, and it becomes kind of insulating state. So there must be something kind of unusual insulating states in that at the 0 Landau level, right? So what is happening there? It turns out that this actually is a good example of this so-called flavor symmetry breaking appears in graphene at a strong magnetic field. To kind of make the long story really short, in the bottom version, I think if I have the 0 Landau levels, there is basically there is a various way that I can just kind of align the spin and pseudo-spin. Turns out in the graphene under the magnetic field, usually A and B around the 0 Landau level is all the eigenstate in the K and K prime, basically sitting in the A or versus B sublattice are separate. Right. So in a sense, sublattice symmetry and the lattice symmetry is tied together under the magnetic field. Right. So you can just represent that how that spin and Dalic and associated is can be just projected in the real space, and how you just put the spins and spin in the real spaces, right? So I think I can just kind of polarize all the electrons into the kind of they put into one of the levels and up, and then the other one is opposite, the other version go down, right? Between up and down, basically you can create this the gap between them, and that can open up in principle that the large insulating states, or you can just align them antiferrometrically, or more precisely canted antiferrometrically. You can just put this so-called different way, calculate distribution, charge density. There's kind of various different way that especially this one is related to how you couple that your spin and the value together, or the sublattice together. You can construct this kind of various different type of system. So there has been some of the proposals that one type of the symmetry breaking state kind of appears into the system. What actually that corresponds to this type of experiment, the insulating state appears, requires a little bit of the further studies, which I'm going to discuss a little bit, but already give you some kind of very early on good example that how the potentially the flavor symmetry breakings plays a role into this ground state behaviors, right? Again, that those kind of things is basically can be explained in terms of the spins and pseudo spins and the entangled kind of textures into the system. Okay, so it's not only this zero, the Landau levels, but turns out that all graphene quantum states strong enough the magnetic field such that now Landau level becomes flatter and flatter. Compared to that your disorder level, the gap becomes larger and larger, and there's not much mixing between the Landau level, and where that now interaction becomes kind of important. I think later that you can see that very similar things that we can apply into the flat band system. Basically here that I can make my band flat by just magnetic field, simple. But nevertheless, it turns out all the integer quantum and fractional quantum, basically their ground, the ground states of all this kind of finite building governed by this kind of flavor symmetry breaking, right? The quick way that you can see that is certain state is stronger than the other states, and then if you just consider all the symmetries, you can quickly see that by just looking at the particle symmetries across this Landau level, you can see that quickly that many of the states that carries this SU4 type of the natures in there. Some of the experiments using this energy sensitive measurement that done by my colleague, the Amir Yacoubis, some times ago, was kind of indicating that all this kind of states appears into each of the Landau level, that understanding this integer and fractional quantum effect on the graphene, basically that the textures of this SU4 spin is kind of quite important. So I'm just kind of giving you that historically, this flavor symmetry plays quite an important role to understand the interactions into the graphene kind of now, if you just accept that now, if this is the Landau levels, either integer and fractions, that flavor symmetry breaking is kind of plays an important role. How about the excitation on beyond of this flavor symmetry broken the ground states? Now, any of the spin system, excitation appears very small, especially in the magnet type of the system. Often that the excitations appears as this Skyrmion forms also. And Skyrmion is basically spin textures that form into the magnetic system. And this is kind of topological object, and it carries some of the topological winding numbers of associated Skyrmions. As a topological object, it contains the Skyrmions and anti-Skyrmions and so on. And it has been kind of quite important, the object that one need to understand that kind of excitation of these magnets. Very similar way, when you have the quantum Hall system, and then the quantum Hall system has the flavor symmetry breaking, or that often we call that the quantum Hall ferromagnets, that those excitation of the quantum Hall ferromagnet also carries very interesting, or the structures like the Skyrmion-like structures, and it has been discussed already early 90s, shown there at all, and showing that in quantum Hall system, also quantum Hall ferromagnet, the basic excitation of the quantum Hall ferromagnet can be understood in terms of this appearance of the Skyrmion into the system. Unlike these magnetic Skyrmions in the spin lattice, this quantum Hall states, this Skyrmion is appearing at the spin excitations, and this Skyrmion also carries the charges. So it turns out in many cases that elementary charge excitation in quantum Hall ferromagnet also appears as spin textures comes as this Skyrmion forms, and the underlying spin texture of the Skyrmions kind of depict this nature of the excitation, charge excitation as well. One way you can understand this one a little bit is the following way, right? So let's say that I have the one of this Landau level, it's a spin polarized. So let's think about this is some sort of the flavor symmetry, simplistic. Then upper Landau level is spin is upper diffractions. One of the charge excitation ways I can do that is across this Landau level. It's then I can just make the one charge is excited, leaving the hole behind. Right? The hole has a missing spin. Now, in terms of spin, it's a spin upper diffractions. Of course, now I have the one spin sitting into this excited Landau level, right? In the simplest mind here is I just kind of take the energies to this energy gap, as well as I have to flip the spins, right? Under the magnetic field to create this this spin polarization, I have to still kind of consider Zeeman energy. Often it is much smaller than this Landau level separation, but nevertheless there is a Zeeman energy you have to think about, right? And the more that I just kind of flip the spins around, the more that I have to kind of take the Zeeman energy, right? However, if the Zeeman energy is really small, right, and then that if you just consider electron-line interactions, right, in this the ionizing electron that you want kind of the holes nearby just to gain the same spins nearby to gain this exchange energy, right? So what we want to do is therefore that making these spins not flip at once, but spin is gradually flipped such that we can gain these exchange energies out of this one. So there will be competitions between the Zeeman versus the exchange energies, and if the Zeeman energy is small, and there are more and more spins got tilted and give you some of the textures into this spin polarization to make the discharge excitations. And that's a way that we can create this exciton into the system. The experiment how we can detect this is following. Because of each excitons now just kind of contains many spin flips around there, right? Effectively, if I just measure the G factors, how many spins got the flip, I should be able to just get this sense that how big is this Skyrmion should look like. And of course, applying the magnetic field, I can just detect the Zeeman. But the problem here is applying the magnetic field in the lambda level, basically, so I change the gap size and so on, right? So there is a better way that I can only couple with the spin to the kind of field. One way that you can do in the two-dimensional system is applying the magnetic field in plane. That often just if the system is so thin, then orbital effect becomes small, and spin the magnetic field only couple with the spin kind of effect. So the way that usually the experiments is to do in this way is just basically tilt this sample under the magnetic field and control they apply the magnetic field such that you keep the perpendicular magnetic field constant, and basically changing the in-plane magnetic field component such that in-plane magnetic field only couple with the spin, and how the energies that often can be measured by the activation energy measurement with the temperature variation and so on, but detect this energy of the excitations by just as a function of in-plane magnetic field, and that will give you basically the G factors that we can just kind of obtain there, and from there on that we can see that what is the size of the Skyrmion look like. In gallium arsenide, where that typically that you are dealing with only the spin, single layer gallium arsenide, you just deal with the spin. But once you get into the especially odd numbers of the even numbers of the states, you just odd numbers of the dealing, that you get this spin polarized lambda levels, and there that you just do the experiments. Then you see that initially the G factor is very, very large, which means that you flip the many spins. But once you increase the magnetic field more and more, eventually Zeeman energy contribution becomes bigger, and the size of the Skyrmion becomes bigger, smaller, and eventually that only one spin appears in the high enough magnetic field, such that G factor gradually changes from the large number to the small number. And often this is the signatures of the formation of the Skyrmions into the system that we're looking at this the state in this physics. Similar way that monolayer graphene, if you just do the experiments, again, the potentially spin polarized states, you can see that G factor kind of changes with the in-plane magnetic field. Again, very similar way that you can create this type of the Skyrmion structures in there. And here, particularly the Skyrmion from the spin sectors can be detected by the applying the magnetic field. Right. So whole point here is again in this flavor symmetry broken states of the states. Basically, you expect to see that also this Skyrmion type of the excitations, which often that give you some of the textures into this underlying the polarized states. Okay, now this is kind of a little bit longer way, but now let's kind of bring our discussion into the twisted system. So we'll kind of hear the many talks throughout the school about the twisted system. So I will kind of give you a little bit of the brief view, but leaving the other details for later lectures also. But the important part here is by just putting this two-layer very similar lattice or exactly the same lattice with some twist angle. One thing that is approximated the quasi-periodic structures, especially if you coarse grain out all the atomic detail, that will give you some tens of nanometers length scale of this more superlattice, which can modulate the band on the top of this atomic scale of the lattice, the band that you obtain from the atomic lattice. Often this one is a way that you can manipulate it or engineer your band into the with this additional periodic structure. So that's kind of what made this field really exciting in the past probably 5 years or 10 years of the time. What is interesting part here is that if you just choose this the twist angle right in the graphene cases, so for this magic angle twist bilayer graphene, somehow initial experiments reported by the Pablo Javier's group at MIT showing that seemingly there's no gap into the graphene system, and put the 2 layers, I don't expect the kind of really gap opens up. Especially in the partially filled molar band, but half here and even quarter here, they start to see that new insulator developed into the system, and then doping this insulator, some of the doped insulator becomes a superconductor, and that's kind of really made the things exciting in this field. And we want to kind of understand what is going on there, and that's in the past 5 years, 4 or 5 years now, we gained a lot of the understanding what is going on into the system. That's kind of one of the major part of this school discussions. In the nutshell, that what we understand now is basically this magic angle is special because that's an angle that one can make the band extremely flat. And initial the discussion was that this researchers McDonald in the 2011. Basically, even in the very simplest single particle pictures, that at the kind of right at the magic angle about 1.1 degree, that considering the interaction between these 2 layers, you can just kind of make that this a flat band exactly sitting at this near the zero energy of this K and K prime point, and this flatness of the band promote the interactions between these carriers, like these electrons holes in the lambda level. That will just kind of give you some of the strongly correlated effects, such as correlated insulator and potentially this superconductor obtained by this correlated insulators, right? But already in the previous example that I just kind of went through the long introductions, this flavor symmetry is kind of still here, right? And it's still that you have this flat band formations, the both and K prime, right? And therefore, this the valley symmetry or the valley the degree of freedom is something that you have to control as well as the speed, right? So you can immediately see that what I just kind of mentioned about all this flavor symmetry breaking the quantum Hall ferromagnets, they play kind of quite important role to understand this the flat band type of the system. So that's something I want to discuss a little bit more. Okay. By the way, up to here, any questions? All right.
Actually,
yes, please go ahead. Yeah.
So this is related to magnetic Skyrmions.
Yeah.
Because I'm looking at the Wikipedia page, it seems like it has this circle configuration, and the Austin has this kind of configuration.
Yeah.
So I was wondering, what about the general form of the potential? Because as I know, it's within the symmetry, we've been doing this quite before. So the one on the circle gives you the Goldstein mode, which is massive excitation.
Yes.
The one on the side gives you the massive mode.
Yes.
So it's like vortex-like behavior. And it seems like by applying magnetic field, you can control, you can kind of move in that makes you can have potential from the massive mode to the massive mode.
Yeah.
So, but because it's SU2 or SU4, is there like a generalized version in complex space of the 5 to the 4 potential?
That's a very good question. Unfortunately, I probably have no kind of grand view on that side. But one thing I pointed out that usually that you see that this nice Skyrmion pictures that also Mexican had, that is XY spins that then also kind of, right? So it depends on what is the nature of this your quantum rotator, whether this is a kind of SY type, XY type or the Heisenberg types, right? Or it's SU2 versus SU4. I think especially getting to the SU4, the generalized Skyrmion, I'm sure that it is rather complicated. Also, all this Skyrmion textures, as far as I know, again, that's that whole literature is there. Also depends on to the dimensionality as well, 3D versus 2Ds, and the kind of there's a really depth of these things. Right. So
Right. I was just wondering, is there like a generalized theory? Because I know like in particle physics, when you look at this kind of structures,
Yeah.
you want to find all the Gaussian mode and all possible potentials, and then your excitations are the Gaussian mode.
yeah,
So I just, my first impression immediately was that Skyrmion must be a Gaussian or something bigger. But as you said, there is a different case, two-dimensional case.
that's right. Yeah, yeah, yeah. So whether this kind of symmetry breaking is a really continuous symmetry breakings that create those kind of things. Is, as far as I know, the quantum ferromagnets, particularly here, that the generating Skyrmion is related with this kind of excitation of the charges. So it is gapped system, gapped mode. So they create usually you also create the Skyrmion and Skyrmion together, and this creating the pairs of this one. Also, it costs energies because I have to create these two charging excitations. Right? It's massive in that
Yeah,
regard.
because I also look at how you generate the spin waves.
Yeah.
So it means like if you make a sort of Lagrangian of this bigger symmetry,
yeah.
then you solve equations of motion that must give you the spin waves.
Yeah. Yeah.
Okay.
Yeah.
I will do it.
Good. Great. Yeah. Great. Any other? All right. As you see that I'm not the expert of all of these things, so I think that it's good that we can nucleate some of the part, right? Okay, on the top of that, basically I want kind of mention that flavor symmetry, there's additional things we have to consider in this battery, and that is kind of related to another copy of this school, right? So one way you can just view that topology is simplest mind, that doing the right topology becomes relevant is the following way. We can ask that, is a graphene really topological? Of course, that's kind of question. So now, how we can answer what something is topological? And usual way that we can look at this condensed matter system is, okay, let's look at this Barry curvatures in your band and whether there's unusual things about the Barry curvatures. So if you just kind of write down the Barry curvatures, equations, and then we can just kind of think through that, compute this Barry curvatures into the graphene band, we can ask whether there's anything unusual, Barry curvature unusually appears in graphene. Comes up, before you calculate it, you can show that graphene is not topological. In other words, the Barry curvature is strictly zero everywhere in the beryllium zone by just considering the symmetry. By just looking at the graphene, that we have the space inversion symmetry and time inversion symmetry in there, right? And then that will give you this the nice relations, the property of Barry curvatures. So to satisfy this one, basically you have to set the Barry curvature equals to zero everywhere in your graphene. So in that regard, graphene is not the topological at all. However, the graphene has been served as a good vehicle to create the sum of the topological model, right? If you just open up the textbook, just to look at how I can just learn about the topology of the band structures, often we start with the graphene and just kind of modify it, right? One way is that you break the sum of the symmetries of graphene and then kind of create some of the topological textures or the states or the Barry curvatures in the system. One nice way is basically break the inverted symmetry. Like instead of graphene, you go to boron nitride, where the two carbon atoms, boron and nitrogen, A and B sublattice are now different. That will open up the gap in the spectrum because now their point is not protected anymore. And if you compute this Barry curvatures there, I think each of the top or the bottom of the conduction band, the valence band, becomes a so-called Barry curvature hotspots, and there is kind of the appearance of this strong concentration Barry curvatures near this point. And though I think that the top all together in sum up, that's still kind of the total the Barry phase in any of the phase goes to zero. That if it's just kind of Chern number is not finite in this case, but at least you can make the sum of this Barry curvature hotspot appears. More exciting part is indeed if you apply, for example, the magnetic field in special ways, take a magnetic field in the unit cell, and that the famous Hardane model also that related with Princeton give you the way that you can also create this the Barry curvatures in the only kind of one side here that you can create the finite Chern numbers. Instead of this stegomagnetic field, you can give it a spin-orbit coupling into this introducing graphene. Then you can get the spin-orbit basically K-Mill models that are creating each of the spin, give you the different type of the Chern numbers associated, spin Chern numbers associated with this type of band. Right. What you see here is basically there is a way that we can create, starting from the graphene, and basically break a certain set of the symmetry, or that kind of do some of the engineering, we can make the graphene becomes topological, right? In some sense, that creating this the twisted layer is a way that you can make the graphene yet kind of topological in some sense. The way that we can view that is, let's say that if I just look at this Brilliant zone and then twist it kind of Brilliant zone, red and the blue here, that together with this, basically you can see that there is a superlattice forms in the real space, in the reciprocal space. Basically now you have that this mini Brilliant zone correspond to much larger the superlattice you have in the real space. Right. So if I just look at this mini Brilliant zone, this mini Brilliant zone now can mimic this kind of larger Brilliant zone we had, like the kind of same hexagon. But one difference here is this mini Brilliant zone consists of the same K value from the graphene, right? So basically it consists of the same chirality within the Brilliant zone in this mini Brilliant zone. Of course, the other kind of big graphene value that becomes opposite, but nevertheless, each of this Brilliant zone collect same chiralities in there, and then there is a possibility that one can just kind of have kind of chiral Brilliant zones in this type of structures. One can do this language very more formally, which I'm going to kind of skip through again. Hopefully, later that can be covered. But important symmetry onto the twisted graphene is basically you can still preserve this twisted and the McDonald model in the languages. You can still kind of preserve the C to T symmetry into this system, and the Chern number plus minus is a good quantum number, which means basically this and this basically has opposite Chern numbers, C1 and -1, and you can just construct this your system. Considering this both kind of preserve the quantum the Chern numbers with the Kn, K prime, and still not and downs all together. So it's all together, basically we are dealing with this again, the flavor symmetries, the related spin and the valley. They're keeping some of the Chern numbers in the combinations. So that's somehow the hidden topology, if you want to say, or the kind of explicit topologies related with this the twisted graphene of the system. Is this really kind of plays an important role? Indeed, I briefly mentioned that when you have this twisted bilayer graphene at the magic angle, when band becomes really flat, and interactions plays an important role. And this, oops. This type of the flavor symmetries that kind of break spontaneously, and that's kind of the reasons that in some sense we get this insulating state into the system. Here is some of the recent, modern experiments that after modern means that initial discovery after 2 years was done by I think Shah Ilani's group in collaboration with the MIT. Showing that using the scanning SAT made of the nanotube, they measure the inverse compressibilities, and this inverse compressibilities is that the jump in inverse compressibility is basically gap opens up, and the size of the jump is related with the energy gaps between this kind of two states, right? And what you see here is a new that we are going to use is basically the Moire filling. So the 4 is kind of full field Moire band, right? And then 2 is basically half field, and 1 is quarter field, and that's kind of the languages that we want to use. Why 4? Because we know that there's a 4 flavor that we have to feed. The 4 flavor coming from the valley and the spin, loosely speaking, right? What it says is every time that we have this integer of this new feeling, basically there's a gap opens up, and that there's chemical potential jump in between this gap, right? It turns out that this gap is related with this kind of so-called flavor symmetry breaking, right? Every time that I have these integer numbers or the quarter field of this Moire band, basically I can feed it up the one of the flavor and that kind of deplete the another one and just keep doing that. So every time near the integer level, basically there's a gap opens up. And in other words, basically there's a kind of some sort of flavor ferromagnetism is happening to create this kind of the correlate the states. It is a correlate state because it's not kind of dictated by any single particle band structures, but nevertheless, the system developed a gap into the system, the gap in the filling, and that's basically give some intriguing the nature of the insulating states. One can study the transport into this kind of gap or nearby the gap, especially under the magnetic field. Often this under the magnetic field. There is the so-called span diagrams that they developed in the, for example, if you measure the longitudinal resistance like RXX or the transverse resistance, basically this is kind of quantum physics that you can measure where gap opens out, what if there's an edge state related to Chern numbers, and you can detect it. You can kind of get the peak of the distance states, that how did this insulating state look like. And the best of the guess that we have so far in the field is many of the insulating states may associate the Chern numbers. Right. Now I would say they already made the work because it is clear that on the strong magnetic field that the certain state is more stronger than the other one. So we can assign the certain kind of more of the Chern numbers into this band. But many of the states did not exist down to the very low magnetic field. So there's a possibility in the low magnetic field that maybe kind of different type of symmetric breakings may happen. But nevertheless, that there's a strong conviction that many of the correlated insulators may contain its Chern numbers. It also dictated by what is a flavor symmetric breaking. Now, understanding this flavor symmetric breaking states carefully is very important because that will depict what is the nature of this correlated insulator, and furthermore, whether how that is related with this the superconducting state that appears nearby. Right. I'm sure that this. Yes, please. Yeah, go ahead. Yeah.
The second question: are there any possibility for the mixing flavor states?
So we have to be careful by what is a mixing flavor states, right? So it could be that spin and valleys are kind of angle between them, and then SU4 that it can just kind of point in any directions, right? That's okay. Yeah. The question was whether there is any mixing states. Yeah. So right. So there, I would say that is kind of one of the SU4, the symmetric broken states, right? Now the system can be break down into the one flavor symmetric breaking versus another flavor symmetric breaking, and it could be equivalent mixed together. That could be kind of different type of things.
So
right?
there would be like a mixing.
Yeah. Certainly, I think when we say that it's a flavor symmetric breaking, or as opposed to say that I say it's a ferromagnetic state, spin ferromagnetic state, or value or states. I mean that it could be really general. The SU4 spin kind of heading for any directions in any angles. Right. Good. Okay, good. And of course, in the past few years, I think this is one of the really hot topics that has been discussed, and then in the field, and you're going to hear them more toward later. And there's been kind of many interest in the correlated states, or correlated insulating state, and superconductors nearby has been discussed. And then there is also good evidence that somehow superconducting state and correlation insulating state nearby somehow is connected, of course, each other. Only the problem that in the field so far, I think there has been some progress though, is that every sample is already different from each other, and this is coming from the fact that when we create these moire structures, there's always some of the residual strain that create some of the disorder into the system, and that's basically some help in the next lectures. To make these things, every sample looks a little bit different, and there's always kind of different type of disorder in the sample. And that makes it kind of the fair comparisons for sample to sample and different condition to different condition. Sample from one lab to the other lab is already kind of difficult. And of course, there's some of this local probe that try to understand the structures very locally. But soon that it turns out that all the local probe reported back that sample is a considerable amount of disorders, especially this residual strains, that angular disorders, which is even 4.1 degrees of the disorder. Already magic angle needed such sharply tuned object. It's a rather difficult kind of make the really general statement. And that has been some of the difficulties in the field. And there's been some kind of progress in this directions, but yet we don't have the really good consensus that how we understand this all the flavor symmetry breaking into this the many correlated states we are seeing, and also how they are related with this underlying the superconductivity. Right. Here comes yet kind of another direction. So I'm going to kind of discuss how much time do I have? 15, 1, 1, 5. Okay, yeah. Into the sum of the kind of different directions, that's kind of going to the multi-layer. And there's a kind of reason that why multi-layer could be interesting. Of course, going to the graphene, twisted graphene bilayer, going to the multi-layer. There are more components in there. The obvious kind of one. The comments is, well, it looks complicated, or in the better, the most going for the language, oh no, it's actually rich physics in here, complicated and rich physics. But there is a kind of practical advantages there. Practical advantage comes from that, well, there are more stuff, so it becomes a bit more rigid mechanically. Therefore, there is probably less chance you suffer from the angular disorder. Well, whether this is true or not, we'll see that in some cases. Here, let me start with this the bilayer bonus stack bilayer graphene. Now, bonus stack bilayer graphene has been also studied many years, and it is actually slightly different from single layer graphene in that sense. The underlying Hamiltonian now it got changes, and instead of the matter is that there are particles, now we have the massive particles that accidentally touch again in the zero energies. But that protections at the zero energy is a rather fragile in a sense that as soon as you break this the symmetry of the system, then basically you open up the gap into the system. And the way that you can break the gap, break the symmetry, the inverse symmetry, is simply applying the magnetic field, the perpendicular to the layer that open up the gap into the system. And it has been kind of used as an open up the kind of rather sizable gap into the system. Now, once you get into this twisted bilayer, the bonus stack bilayer, often we call the twisted double bilayer graphene, kind of more word. But you can just kind of play the very similar games as a twisted single layer the single layer graphene, twisted single layer PVG, twisted bilayer graphene. Instead of you have the dispersion, the linear dispersion, you have the massive dispersions. But advantage here is applying the magnet, applying the electric field. I can open up the gap, but also you can just tune your band structures by applying the displacement field, electric field in the vertical directions. That will just kind of be together with this the layer, the coupling between this the bilayer graphene. There is a way that you can make the flat band formation that different. In a sense, unlike this twisted bilayer graphene, where that the band structure is fixed, your infection is fixed. In principle, here that using the displacement field, you can control that your band structure, band dispersion, such that always kind of try to bring into the near this the flat band conditions by controlling the displacement field. Indeed, that's kind of the cases, and here's the experiments were done in the microwave as well as similar result from the MIT. It shows basically similar things, but I'm showing you the back gate and the top gate changes, and this line is basically charge neutrality line. I'm plotting out the resistance, and this dark red means that it's highly resistive, and then it's more conducting in the this charge neutrality point. And this is basically nothing but going here. That you have open up the single particle gap, as I mentioned, they're applying the electric field, open up the gap, becomes insulated. Now, here, this is basically this line is a full filling line, and you get another insulator. Again, if you have this full field models and turn on the interaction between the layer interaction, even the single particle pictures, you can open up the gap, and then opening the gap here is not surprising. What is interesting part is that this half field, the model band, often we call the nu-2 cases, there can be the gap opens up only in the finite displacement field, potential actually, when you make this band kind of flatter with some displacement field, basically I start to create this so-called correlated insulator state in the half-wave states in this way. Right? You can study that those kind of the conductance. If you let me skip this one and look at this also charm number distribution and measure mass. It turns out that nutshell is here is this the U equal 2 half-wave water band is also kind of correlated states, correlated insulating state. They like the single layer of the twisted bilayer. Right. So it's actually interesting. But now let's try to ask the following question: that is this system also some sort of the flavor symmetry broken states? One way, simplest way that we can just use is kind of graphene quantum ferromagnet. Is that what about that we apply the in-plane magnetic field only coupled with the spin, right? It happens to be these spin polarizers, that is spin textures. We may be able to detect that the nature of the disinsulating state. So let's take the disinsulating state, and then this axis is based on applying the in-plane magnetic field. What you start to see that is the half field, the insulating state becomes stronger. I think this is darker color in the insulating, right? We can show that even the gap is increasing in a moment. So that we know that somehow under the magnetic field, the gap is larger, right? And even so, that this polar field state also insulating state appears only at the finite magnetic field in plane, right? So all these things indicating that both half field and polar field somehow there is this polarized underlying the states in there where the gap is increasing or like as increase the Zeeman activation. So this tells you that at least that underlying the broken symmetry onto this twisted double bilayer is somehow that there is a significant spin sectors got involved in the polarizations which actually react with this underlying magnetic field, which is a little bit different from, by the way, the twisted bilayer cases. A little more detailed studies in terms of the connection with the Hall measurement start to tell you something interesting around this correlated insulating state. So this is again spin polarized the gap that just kind of we mentioned. And if you measure the Hall measurement nearby, and typical way is you just measure the Hall and then the normalized Hall density, and this becomes the kind of integer numbers. And then more compare with the model filling. I'm sorry that this supposed negative sign, and mag and PC conversion makes this weird symbol. And this difference and this so-called X number is a very important number to give us that kind of how many field band underneath when I kind of give you this charge carriers. And this finite F means basically there's a flavor symmetric breaking is happening. And this is kind of one way that nicely designed in the past few years in this twisted bilayer businesses. And then one way that you can easily get whether the flavor symmetric breaking is happening by just measuring the Hall measurement and compare with the model filling in terms of the integers, right? So what you just do that is if I just kind of plotted out this field band with the Hall resistivity. So around this the halo that around this halo that surrounding the spin polarized states, you can surely see that it's the field inflections, field band number is equal to 2. So there's kind of flavor symmetry is breaking there, right? And around this insulating regions, and that's where that we get this kind of somewhat interesting behaviors. All these things basically indicating that this near the spin polarized band, the gap, the doped state is again related with the spin polarized ferromagnetic and metallic state kind of, right? And so this is another good example, right? There's a superconductivity that creates a doped correlated state. In this particular cases, there is some sort of ferromagnetic metallic state appears near this spin polarized gap. I think that's kind of one good example. That again, away from the twisted bilayer going to multi-layer, that you start to see that something interesting appears in the different manner of this magnification realizations of this correlated state. Now, yes, please.
Why at the negative it doesn't have?
So many of the band structures of the twisted bilayer and even twisted double, even most of twisted double bilayer, there is whole symmetry is wrong, of course. That's a related with the second year. Hoping to know. Right. So, because especially in the case of double binary, the particle method. Good. But this can go on, right? It comes out, by the way, it's a twisted over by there. There are 3 or 4 groups now, and 5 groups that are doing the very similar experiment. They see the very similar. It's a little bit different story and twisted bilayer graphene stories. Part of the reason we believe is okay, so there are already 4 layers, right, altogether. They give you a little bit more rigidities that just ease out that it's the residual strains. That's a speculation, but anyway, that's observation is that between different groups, they're reporting kind of similar things. Of course, we can just push this even further, right? Going to the multiple layers, right? So there are many different ways that you can make this multiple layer. One way that proposed by theory by the Aslan Kalab and actually this one is basically stacking the twisted layer into the alternating fashions. In that regard, basically, preserves certain symmetry, especially this symmetry and some of the systems. Turns out, if you just go through this very beautiful theory, there's one simplification one can make, at least if you just look at only the low end sector. For example, if you have the 3 layer with alternating stacking angle, basically decompose into this tool the 1 twisted bilayer together with this 1 monolayer of the graphene. Although there's a renormalization of the twisting angle, the stacking, the interactions that considering this twisting angle. But nevertheless, I think this they provide the general tools that you can generalize this stacking way. Twisted bilayer, trilayer, quadruple layer, and even quintuple layers that you can go on. Basic rule is if I have the odd number of the stacking angle of the alternating, you always have the 1 at least the twisted bilayer like this the band structures with the 1 Dirac cone in there, something like this. Let's see, the tri-layer cases there is the Dirac cones there and the 1 flat bands there, and then if you have the even number of the layer, you have the flat band with the kind of this cut this of this TBGs. But usually other TBGs not at the matching angle will give you a rather dispersive relation, right? So practically what happens is when you have this the even number of the layer, there's if you just kind of tune your band in the flat, the other band becomes more dispersive, and near the zero energy they have shows often the Dirac cone like the dispersing with finite the velocities at this cost. So that's the
So the flat bands are not really isolated.
That's right. In that regard, that other than twisted bilayer, basically there is no gap in the cycle, right? So there is always another band that either Dirac like the sharp, Dirac like the cone, or that already more dispersive band, but they're all kind of close. So in that sense, you are not getting insulated in that regard, right? Although there is a way that you can still create the gap, especially the odd number of the layer there is no gap opens up or whatsoever, but the even number of the layer, once you apply the electric field, this displacement field, somewhere in the spectrum, you may be able to create this gap. Because with the electric field, they start high. Okay. This has been seen also, of course. The field is progressing really fast between the experiments and the theory. The theory papers came out and the experimental papers, the time difference is only weeks or month. And here's one example. So you just kind of put these 3 layers together. And then, of course, you have to put this exactly the same angles for the alternating angle. Experimentally, it's not exactly possible. So the top and middle layer and the middle and the bottom layer, there is an angle difference between 1.35 and 1.66, about kind of 0.3 degrees of angle difference. But amazingly, that if you just make the overlap region, if you just measure the transport is clear, and angle is somehow in average of the between the 2 layers, right? So you can see that even if the experimentalist was not be able to just match exactly, somehow in the middle layer, there is a kind of locking mechanism. They tend to align it to the sum of the average angle. Meaning that again, that some sort of lattice interaction, the relaxation that is quite important role, which I'm going to discuss in the second lectures. Right. But nevertheless, in this middle layer, it looks like all these band structures you can look at there is very similar to what you expect to see in the theories. Basically, there is a kind of one flat band and one dispersive band in this energy scale that I just kind of exaggerate this the flat band dispersion. There are cone that going through is really, really sharply going through in there, and that's basically seen in the transport measurements. Okay, and this type of sample, because there is existence of flat band, although there is no gap, as pointed out, so there is no true insulating state. There is a yet flat band. So near the flat band, basically you see that the superconductivity appears, and this superconductivity is both the electron hole appears and has a little bit more respect to the TC than TBG. Part of the reason is in this renormalizations of the multiple layer, at least in the magic angle side, we have a little bit larger coupling than the three-spiral layer. And that will provide the higher TCs into the system. And then one can see that there's okay, so many of the plot is missing, but okay, but let me see what is missing. Just kind of trying to show you that how that this superconductivity got tuned by the density. So look like a PBG cases, but it's tunable. Let's see. And more important part is also with the displacement field. So I think the previous slide suppose shows, okay, so TBG and then TTG, or this is for layer, at least the superconductivity is tuned in the similar fashions with the distance. But important difference between the TBG and this layer is there's a displacement field, right? Like this double layer pieces that I showed. Displacement field is kind of tuned into a single particle band. So this is an additional knob that we can use. And same thing that this twisted tri-layer actually worked it out. When I just apply this displacement field, there's the hybridization between flat band and this displacement band, and that will start kind of modifying the band structure. Like this got changes, and some of these things got changes. So with this displacement field and the field inflections and again the resistance, this is kind of superconducting states appears. Basically, you can see that there is a tunability that shows up in the displacement field, and this is an interesting tool that we can use to just understand that how the band structures and the superconductivity are correlated and impact on each other. It turns out also displacement field can control the underlying correlated insulating states. Again, then I told you that when you measure this the Hall measurement and subtract it with this refraction, and that is if this becomes integer numbers, if that is a 0 for the integer number, that becomes an unsymmetry unbroken. But that becomes the sum of the integer in between. That becomes the symmetry broken state. I think the color scales on the labels start to shift. This graph doesn't make sense. Looking again that there's a bit of the issues of the mag and TC conversion. So this is if you just kind of shift it off the things. Okay, this amount. You will see that the point I'm just trying to make there is a strong the connections between underlying symmetry broken state and the superconductivity region that superconductivity happens, which can be tuned by the displacement field. Again, that's because I can tune the single particle bands with the displacement field, and tells you following kind of statement. At least I can make the statement. Right. Turns out that U equal to the half the water pattern. Not surprisingly, it is a symmetry broken state, a flavor symmetry broken state. And superconductivity regions that we are seeing is exactly matched with this flavor symmetry break conditions with the finite energy. So that strongly kind of convict that whatever superconductivity we have into the system, whatever mechanism it has in there might be some connections between this flavor symmetry broken states. Now, this idea can be pushed a little bit more, right? So if the symmetry broken state is in -2, that the superconductive dome that I'm showing you here is something like this. So it's the insulating state. Away from the insulating state, the superconductivity becomes stronger and start to drop, so like the dome, like the chips, right? So is there a way that we can also understand those kind of behavior? And of course, there is many the theories can be possible. One of the interesting things, I don't necessarily believe this is only the way, is basically indeed if this insulating state is related with the flavor symmetric gradient, right? And as I mentioned, like the quantum Hall paramagnet, one way you can create this excitation, especially charging excitation of the symmetrical state is creating this, right? And tied together with that, indeed, this symmetric broken state has this charm plus n1 minus factors there that by this combination of this symmetric broken states, you can create these two charge excitations with opposite charm numbers, which actually carries, in some sense, opposite helices of the Skyrmions there. There's a mechanism, at least in the theory, that kind of creates this Skyrmion interaction induced in the Cooper pairs. Basically, can be created, right? And simple estimations out of this, the kind of Skyrmion mediated interaction theories that give us the way that you can compare with how the TC got modulated with the density, more like to give us kind of visual estimations based on experimental observation. Right. So this type of thing is one of these attempts, at least that can we actually tie it with this superconductive we observed in the system with the some of the flavor symmetric gradient. Of course, there is a long way to just go to really show that whether this is really the right mechanism, but already kind of start to show that there's many kind of different recipes we can arrive here that combining this flavor symmetric breaking versus that kind of the superconductivities. All right, so I think that my time is almost up, so let me just kind of skip through this rest of things that I just prepared, but story is kind of very similar. You can just expand this going to multiple layer. The experimentalists already come up with a 3-layer, 4-layer, 5 layers. I think maybe even working on the 6 layers, right? Going to this multiple layer, that you get this much more rigidities, as I mentioned, right? But also the difference between the different lab and different sample becomes less. I think that's kind of important part. And there's always this displacement field of give us a way that we can tune the single particle band, right? And then study about that, what is broken symmetry states in there, and how that is connected with the superconductivity. That always kind of provide us that useful experimental knob that we can just kind of look at this underlying mechanism of the superconductivity. I think that nice thing, the last word that I can give here is nice thing about this twisted system is basically we have a lot of knobs that we can just tune around, which actually affect both of the underlying broken symmetry state, as well as some of the correlated states, like the ferromagnetic states and superconductivities. And I hope that this type of experimental knob, as well as the theoretical knob, allows us to at least kind of prove, say that potentially the correlated states like the superconductor comes from unusual interactions underlying the system. All right, so that's all that I want to say. I'm happy to answer further questions if you have. Yeah.
Thank you, Professor Kim. And we first take in-person questions.
Yeah.
And we'll raise your hand and pass microphone.
Yeah.
Hi, Ernest Hall. I wonder, there's a lot of study of like alternating multilayers, for example, alternating. Is there any interesting things happening in concept with the
Constant kind of
like one way and then
yeah.
Like,
right. I think so yes, I think there is experimental theoretical studies and then also experimental study even for the not alternating but kind of successive the twisting. It turns out that experiment is a little bit harder because now you have this you can think about this as moire, and then another layer is a moire, and moire, that the size tend to be larger rather than contained with a certain the finite length scale. So usually disorder plays much more the role into this realization of the system. So experimental is harder experiments. theoretically, what I heard is that basically the successive angle, you tend to lose this C2T symmetry. So basically it becomes kind of quickly lower symmetry classes. So unlike this alternating the angle, theoretical discussion is really kind of widely speculated. As far as I know, that there's no kind of strong claim that can make in the theory. Experimentally, it is harder system. By the way, this is Xiaomeng, who was yeah.
So you mentioned monolayers is not topological, and you know, basically better is topological, and there's degree of existence is like all that model is topological. But monolayer have a pi barrier curve, right? So you don't, like I always thought all other systems based on graphene have their topology originally from that pi barrier curve.
That is probably right. I think although that the strictly if you just compute the Berry coverage is always 0 as a symmetry argument. There's one unique point is right at the K point, right? You can think about if I just make these arbitrarily very small gaps there, then basically you have the infinitely kind of very large Berry coverages concentrated in Kn minus negative K prime, right? So in some sense, it is kind of topological. It kind of carries this the seed of the topology is in there, right? But right at the key point.
Thanks.
Thanks a lot for the very nice talk. I also have a question about the multilayers.
Yeah.
So do you also find that it's easier to fabricate these than twisted bilayer? So there's really some self-locking mechanism.
Yes, I think so. That we have the better yield than the twisted bilayer for sure, right? Now, self-locking mechanism, we have to very be careful in some sense. Which has not been kind of completely proved. That I think there's I think the next lectures I can briefly show. I can show it now. That's better. I think the best one is it's also not experimentally completely proved. This computer is already slow to load it, but hopefully that it can. Okay, so there's a STM study shows that indeed there is additional structures appears. There's a TM study shows that there may be more and more of this not self-locking this kind of part. But nevertheless, I think there's interactions that drive the sum of this majority of structures into this average angle, right? As long as if they are not too different from each other. So there's a way that you can tend to create this a little bit more homogeneous samples in that regard.
So even for 4 and 5 layers, etc.
That I don't know. I think at some point you start to lose all these things, right? So at least 3 layer and up to 4 layer. I think that if I just look at this the data from the other groups as well as my group, I think there are more of this the similarity between them. I think generally. I think statistics is not too many at this point, but seems like that's the way. So there must be some kind of optimizations, right? You cannot go probably too large numbers eventually, right? Because every layers will just kind of give you uncertainties, right? So there may be something that maybe 3 layer, 4 layer, maybe 4 layer, because 4 layer, in fact, applying the electric field, you can open up the gap in somewhere. The 3 layer, you don't open up the gap. So 4 layer, maybe it's a kind of good, the optimal that you have the certain gaps. You may have the robust superconductivities, reasonable chance of getting this with typical yield.
Okay, so I get the impression that there are always like flat layers and they kind of on top of each other and people question how many layers it can go. So maybe it's a silly question. I was wondering if people could take 2 layers and kind of make different topological structures, like kind of a cylinder or toroid, and if that would affect the superconductivity and
Wow. You must be curious. Right. Yes. I think in principle it's possible. I think indeed. So I did my postdoc with Paul McLean, and Paul McLean as the few 2 years ago when I just met him, that talk about this exciting twisted bilayer. And we discussed about this kind of new, maybe you can just go for the different topology rather than plane. And he pointed out, yeah, that exists. That is nanotube. Actually, if you go to multi-one nanotube, you have the various different chiralities and it's the cylindrical shapes. So at least that certain part, the nanotube type of that things, cylindrical type of the topology exists. People try hard to make this a torus of the nanotube, which is yet kind of more better at the topological object. I don't think any chemist has succeeded yet, not mentioned. But pokeballs exist. Basically, that's a sphere. So there are some of these things that do exist in chemistry lab. So I'm sure that interesting things can be said. To tell you that, in fact, there has been some paper I've been seeing that at least people already look at this the two-shell multi-wall nanotube with the slightly different chiralities and kind of discuss a very similar thing of this twisted bilayer system with some incommensuration between them. So you can find some of it.
Yeah, because kind of gives some room for imagination. If you have a tube, you can send magnetic field inside and see how it affects. Like the configuration of magnetic field really starts mattering.
I'm sure that if I just kind of go into the joke that my wish list of the chemistry is 2 graphene layer connect with the carbon nanotubes and seamlessly. That's a basically black hole and white. There is theory out there about it. No chemist has succeeded.
Maybe we will take one question.
Yeah.
Yeah, this one question is from Princeton and asking Professor, how can one stabilize these twisted layer structures, especially if more layers and colors are involved? Thank you.
Yeah, that's a practically difficult question. I think that the world expert on that part is sitting there, so I will just defer to Symmetry and how to stabilize without relaxation. Yeah.
Two layers again.
How to stabilize the twisted layer structures?
Yeah.
When you have more layers and having.
Oh, I mean, experimentally, we unfortunately don't have too many control.
I know that is answer. Yes, yeah. I think, the most of the failure mode of the sample fabrication is they tend to relax it back or kind of move away from the targeted angle. And since Van der Waals system is rather slippery, right? So that's where the difficulty comes from. So there's various way that you can try to pin down the lattice and during the fabrication. Yeah.
Well, one thing I guess many groups try to do is they try to anchor the edges of the devices. So the edges of each graphene layer, they like to hook to one another when they're assembled. And that gives you a little bit of stabilization. But of course, it doesn't remove the strain patterns inside the graphene film, etc. So yeah, I mean, but I think people like Corey Dean, they twisted with
rotated,
right? Yeah. And there they can make sure that sort of the sample relaxes the strain during the sort of rotation process. But that technique also is very difficult. Okay, last time the speaker again.
Thank you.